Power is abbreviated with a capital letter P. It's measured in watts, abbreviated capital letter W. It's not an entity of itself. It's really just a combination of voltage and current. So if you have flow and pressure, that's an indication that you have power. Or another way to say that is it takes power to have flow where there's maybe high resistance to flow, because you'll need some high pressure. So you'll need voltage and current. In other words, you'll need power. Some other examples might be if you have no resistance, it really doesn't take much power to push a lot of current through. So just to give you a sort of a flavor or a feel for what power is, you can do lots of examples. Maybe I could say, do you have a powerful car if it can go fast? Oh, but I forgot to tell you, it goes fast downhill. So not necessarily powerful, right? Or I could say, do I have a powerful car if it can go downhill? Um, or do I have a powerful car if it can go uphill? I'm sorry. And maybe not, maybe not, because I forgot to tell you that when I'm going uphill, it can go uphill, but it's very slow when it goes uphill. So in other words, I'm trying to put two things together for you. You have a powerful car, perhaps, if it can go fast uphill. Same thing. If that analogy helped, or I don't know. But yeah, so it's not a new entity of its own. It's just power is just a combination of voltage and current, and we can write it as P equals V times I. And now we have all together, we have our original, voltage, current, resistance, but we're going to add power into the mix. And the bottom line is, if you know two of these four, then you can solve for the other two with algebra. So let's look at how that happens. We have our formulas now, V equals IR, and now the new one is P equals VI. These are the different algebraic arrangements right here. For V equals IR, of course, you can push things around algebraically and get those variations. And P equals VI, of course, you can push that around algebraically and get these variations. Some people go nuts memorizing all of these, that's what I had said before, about not trying to memorize everything, just understand it. I would say, make sure your algebra skills are up to speed. I mean, if you're a little rusty, go to the math lab, work on your algebra, but you only have to memorize two formulas. I mean, I wouldn't even say memorize, but I mean understand two relationships here, right? And then it saves you having to memorize six things. So I think maybe students do, if you have to memorize something, they might memorize that, they might memorize this as far as relationships, but then just work things out algebraically. Another maybe two things that probably save you time if you do have them in your head are these relationships. It's true that power is just voltage times current. That's all it is. But when you start combining these formulas, you can come up with we can come up with this one here, and it saves you time from doing the algebra if you just know this relationship. Let's show you how we derived power as also being equal to current squared times resistance. It's real simple. Maybe I'll change pen color here so you can see the derivation in a different color. There you go. Okay, so how do we know that we know power is equal to voltage times current, but how do we know that it's also equal to current squared times the resistance of the path? Well, we just did substitution. So we took the fact that V is equal to IR. So that means, of course, if they're the same thing, I can take IR and substitute it in for V. And then I get this new equation, yeah, power now is equal to I R times I, right? And then I'll just gather up the terms, right? That's two I's. I times I is I squared and R. And there we have it. Power is equal to I squared R. You don't have to memorize that power is equal to I squared R because you could always derive it with substitution. It just saves you time, and we do it so often that I would say a lot of times technicians are going to have I squared R right in their head. You want to know how much wattage a certain load or path or a certain device with a certain resistance and a certain current flowing through it. You want to know the wattage that's going to be generated, or the heat perhaps. It's I squared R. So that becomes real familiar to you. And let's derive this other one. You know, how do we get the fact that power is equal to V squared over R? Same game. We're going to take the fact, we're going to do substitution again, but we're going to substitute, here we are. Let's look up at the very top here. I is equal to V divided by R. So those things are the same thing. So I can take V over R, substitute it in for I. And now I'm getting this equation. Power is equal to V. That's the V. And I'm substituting V over R for I. See this here? I'm substituting V over R for I. So putting that in there. So that's V and then over R. And I can rewrite that as V squared over R, right? Okay, so that's how we got this. And altogether, like I say, those four, if you are going to have something in your head, you know, that one, that one, that one. Typically, those are probably the ones that are in your head all the time. And even though you can derive these, it saves you time having to derive them. And we'll do some example problems with these to let you see how useful they are. But you can probably see like this one here is an example where you have a certain device and you're going to power it up with a certain voltage and you want to know the wattage. Well, right there, whatever voltage you connect to this device, V squared, that voltage squared over that device's resistance tells you how much power. So, right. And all things, you know, have their limits as far as maximum voltage, maximum current, and maximum power. So, because if you have too much voltage and current, then you'll get too much power and it'll burn up the component perhaps. So these are things that we're always considering. So now that we have power in the mix, we always have to keep an eye on all four of those properties. You know, this is really a component property, and then these things here, voltage, current, and power, those are what you're subjecting the component to. Or so, in other words, so you have to always keep an eye on what would be too much voltage for that component, what would be too much current, what would be too much power, which means at times you might not exceed the voltage or the current rating of a device, but the combination of voltage and current could result in exceeding the power of the device. So we'll be doing that a lot, and boy, that really is what turns you into a technician as opposed to a hobbyist. As a hobbyist, I remember burning up a lot of things because I wasn't paying attention to this. I might know that, hey, it can only handle a certain voltage, can only handle a certain current, but then I forgot to take into account that the combination of the two, voltage and current, is what did that component in. So, okay, we'll do some practice problems in another video then to help really clarify the usage of this now that we know all four.